today is a nice day. We're going to take the last two topics we've talked about. So you might remember, what are the last two topics we've talked about? We talked about line integrals, and then we said there's this thing called the del operator. And we're going to try to merge them together. And at the end, we're going to see it's really quite beautiful. And by the end, I mean in about 3 or 4 minutes here. So let's start with the fundamental theorem of calculus. What our goal here is to do is to say, you know, this fundamental theorem of calculus is really useful. Now, how do we think of the fundamental theorem of calculus? We say we integrate from a to b of some function, and for simplification, we'll write it as f prime of x. And to get this integral, we evaluate it at the endpoints of some other function called f, where it's more or less the antiderivative. Now, there's a way to think about what's happening here, which is to say the following. I want to understand something about a function over the entire interval between a and b. And the answer is to say, well, to understand this function, you have to understand the related function, but at the boundary of the interval, which in this case are endpoints. So we're going to have this same theme showing up over and over again. Indeed, we have, including today, there's more or less 5 main let's talk about new material days left in the course. 4 out of the 5 days are, let's think about ways that we can generalize this notion of, I want to understand a derivative on the inside, I just need to understand something else on the boundary. So today is one of those days. So we want to do this for line integrals. And we say, okay, so how do we get there for line integrals? And the question is, what's the right thing to put here for the derivative? Now, from last time's discussion, we should say the right thing to put in for a derivative is the gradient. Because the gradient is sort of a derivative, and it works for our vector valued functions. And so that's where we're going to go. Now, if we start here, we're going to apply the chain rule. So I have here my function. So this is my function. Now, my function originally is a function of 2 variables. So the picture for the chain rule says my function is a function of 2 variables, x and y. And then x is a function of t, and y is a function of t. And I'm asking the question, well, how does this change as I change t? So we apply the chain rule, and we say, well, you take the derivative of the function with respect to x, which is partial f partial x, times the derivative of x with respect to t, dx dt. And that's one way it changes with respect to t. But there's a second, which is you take the derivative of the function with respect to y, partial f partial y, and you multiply that by dy dt. Now, if we stare at that for a moment, we say it kind of looks like a dot product. So if you remember what dot products are, is you multiply 2 pairs of vectors and you add up the results. So here what we can do is we can say, well, let's pull the partial derivatives of f into one vector and the derivatives with respect to t into another vector and take the dot product. So lo and behold, it turns out that we can think of the gradient of f dot dr, which is what these 2 things become, as corresponding to the derivative of our original function. And now we're in good shape. So here we go. We have some parametric curve. We're going to have x of t, y of t. That indicates our location. Time is going to go between alpha and beta. And the reason I'm using other symbols here is I want to sort of introduce this notion of I have the time parameter, but I also have a location. So at time alpha where I start, I'm at point A. At time beta where I end, I'm at point B. So A and B are my start and end. So let's see what happens. So we want to compute the integral of the gradient of f dot dr. So this is a type of integral we were talking about for line integrals, where we were doing something where we had like m dx plus n dy. That's the type of integral you have here. So in particular, if we had the gradient of f, where happens to be some vector valued function mn, another way to write this integral along the curve, gradient of f dot dr, this is the integral along the curve of capital M dx plus n dy. So this really is the type of line integrals we talked about before, where we said, okay, put everything in terms of your parameter t. So we do that. We put everything in terms of our parameter. Well, gradient of f dot dr, that's easy. That's the derivative. So if I want everything in terms of t, it's the derivative of f of x of t, y of t. And I have to put my time, my bounds in terms of t, alpha to beta. Easy, easy, okay. Now what? Well, we're integrating a derivative. I know how to integrate a derivative. It's just the original function I started with. So there we go. So I get that it's the function f of x of t, y of t. Then I evaluate from alpha to beta. And what do I get? Well, if you plug in beta, you're going to get x of beta, y of beta, which means you're going to be at your point B. You're going to be at your endpoint. So it's the function at the endpoint. And if you plug in alpha, x alpha, y alpha, that's your location where you started. So you're going to get your initial point. And so you get the function at B minus the function at A. Now, one thing that should be noted here, and we want to say this multiple times because it's going to grow ever more important the closer we get to the end, is orientation matters. So what we're talking about here is we're in our plane. So we're starting somewhere, and we move along the curve, and we end somewhere, but we definitely move with purpose. In other words, I'm going from A to B. There's an orientation on this curve. And so what we always want to make sure is you take the function at the end point, subtract the function at the initial point. So orientation matters. Now, what would happen if I changed my orientation? What would happen to the answer? It would change the sign. So when we talk about orientation, ultimately it always comes down to what's the right sign. And so you might say, well, I'm only off by a sign. How much could that cost me? The answer is 1 point. You don't want to lose that point. Got to get them all. Got to get them all. So the punchline for today, our big takeaway message, is that when we want to do integration of conservative functions, in particular when we talk about integration, we're talking line integration, it's easy. So if I have a conservative function, I just have to know my potential function at the endpoints. So what's great about this? Well, there's a couple of things to note. One thing that's great is if you look on the right-hand side, where you have this f of b minus f of a, you'll notice it makes no reference at all to the curve that joined a and b together. Well, what does that say? Well, if you go back to a picture, let's say we have this picture here, it says, maybe you don't like that picture. Maybe you want to go in straight line segments. And the answer is, that's fine. You can go along a different curve now. Because ultimately it turns out that when you're working with conservative functions, it's not the curve that matters. It's where you start and stop. So you get two really beautiful options. So one option to say, if I want to integrate something which is conservative, in other words, integrate something which is the gradient of some other function, I can find that potential function. And if I have that potential function, I evaluate it at the endpoints, life is good. But there's a second option, which says, maybe it's hard for me to find the potential function, but that's okay. Maybe there's a better choice for how to get between my A and B. So perhaps a better curve will work nicer. Now you might say, why didn't we do that in Calc 1, this second option? Well, the answer is in Calc 1 you had no choice, because it was one-dimensional. If I wanted to get from x equals A to x equals B, I had to go in between those two. So here, in multivariable calculus, you have freedom. You get to move around. And with great freedom comes great responsibility. Our problems become a little more interesting. So let's do a couple of examples to get going. Any questions before we begin? All right. So remember, the goal is, if I'm integrating something which is conservative, find that potential, evaluate at the endpoints. Okay. So let's try this. An example. Let's find the integral along the curve the integral along some curve of the y dx plus x dy. Now it doesn't say what the curve is, it does say where we begin and where we end. So we start at 0, 0, and we end at 1, 1. So we start at 0, 0, and we end at 1, 1, and we're some curve. Now you might say, which one? Just have fun. Release your inner artist. Okay, there we go. There's the curve. It goes from 0, 0 to 1, 1. It's probably not the easiest one to work with, but the punchline is we're not even going to work with it because we're going to use the theory. What's the theory? Well, the theory says integral of conservative functions are nice. So we'd like this to be conservative. Now what does that mean? Well, this is written in the form y dx plus x dy. So if we think of this as being m and n respectively, what we'd really like to say is that there's some little function f out there where the gradient of that is mn, which in our case is y comma x. So we have to think, is there some function with this nice property? Well, whoops, let me move it down a little bit. Okay, including the property that writes a little bit darker. That would be nice. So what are we asking for? So I want some function where when I take the derivative with respect to x, I get y, but if I were to take the derivative with respect to y, I would get x. Now why do I say that? Well, that's how they find the gradients. The derivative with respect to x is the first entry, the derivative with respect to y is the second entry. Can we think of any function with this property? Yeah, xy. So it turns out that one function which does this is f of xy is the product, x times y. And now, if you're not convinced, you can check. And lo and behold, it does work. All right, so what does that mean? Well, it says that if I want to integrate along the curve y dx plus x dy, I can take the function xy and I'm going to evaluate. So when you see that long vertical bar, it means evaluation. And here we're not evaluating at times, we're evaluating at points. So you just have to make sure you have your start and end lined up. So we start at 0, 0, we put that 1 below, we end at 1, 1. So you plug in x equals 1, y equals 1 into x times y, what do we get? 1. Plug in 0, 0, we get 0. So our final answer is 1. All right. Well, that wasn't so bad, even though the curve looked terrible. And indeed, you should always be suspicious. Say, you're on an exam, and you say, that's an awfully looking inconvenient curve. I wonder. I wonder. All right. Well, let's try a different one. Find the integral along the curve of x squared dx plus y squared dy for the curve shown below. And, okay, kind of looks like an infinity sign. All right. And we start and end at the point 4, 0. So there's a little mark here. So this little mark is indicating the point 4, 0. That's where we're going to start and end. So let's think about this. Probably the same idea should do it. So we're looking for a potential function. So the x squared, this is going to be, we hope, what we get when we take the derivative with respect to x, and the y squared should be what we get when we take the derivative with respect to y. So what's something, let's just start with the x squared. What's something that when we take the derivative of it with respect to x, we get x squared?
X cubed.
Almost x cubed. 1/3 x cubed. Yeah, you have to account for that 3 coming down. So it's like, we think our f, it better have 1/3 x cubed. Because you better get to the point where when they take the derivative with respect to x, we end up with x squared. Now when we took the derivative with respect to y, we want y squared. Well, what does that say our function also needs? Yeah, 1/3 y cubed. So we say, okay, so maybe this will work. And how do we go from maybe to yes? Yeah, we just double check. Gradient of f, well, derivative with respect to x, Okay, that would be x squared plus 0, which is x squared. Derivative with respect to y, that's 0, and y squared. Ah, good. We are happy. All right, even if we can't do a very good happy face. But okay, we're happy. Good. Now, what does that mean? Well, we're almost done. So here's our curve C, and the integral along this curve, x squared dx plus y squared dy, is going to be our function 1/3 x cubed plus 1/3 y cubed evaluated from, well, where do we start? 4, 0. Where do we end? Same place, 4, 0. So, what does that give us? Well, 4 cubed? 64 over 3. 0 cubed, 0. Subtract, okay, so 64/3 is when I plug in 4, 0. Now, what do I get when I plug in 4, 0? Yeah, still 64/3. In fact, we should have been, wait a second, I'm going from the start to the end, but the start and the end are the same thing. So what's going to happen to our answer? 0. And in fact, one of the ways we could have seen this is say, hey, you know, if I have the same start and the same end, let me change my curve. So instead of a curve that's going to come out and loop around and come back, my curve could be the curve that just stays put. That also has the same start and end. And the same start and end, as long as I'm conservative, the answer is the same. Well, if you do a line integral for something that doesn't move, there's nothing there. Nothing there. All right. Which is what that says. If you integrate along a curve that's closed, where the start equals stop, and you have a nice function, you're going to get 0. Now, so far we've been pretty lucky, and we could just sort of eyeball and say, yeah, we can guess it. But we want to be a little bit more than just lucky. So we want to be able to look at something and say, this function, this is conservative. And the next thing we like to do is to say, and here is the potential. So how can you test if something is conservative? All right, here's what it comes down to. You think about where a conservative function comes from. Conservative function corresponds to taking a gradient. And gradient consists of partial derivatives. And what you want to check is to say, are the partial derivatives themselves consistent? So if my function is conservative, then the first entry is the derivative with respect to x, and the second entry is the derivative with respect to y. And to check if they're consistent, I say, okay, let's go one step further. A little bit further down the rabbit hole, if you will. So we're going to take the first entry, take the derivative of that with respect to y. And if you do that, it's a derivative of a derivative, which means it's a second derivative. It's f, then with derivative with respect to x, and then y. Go to your second entry. Okay, now I'm going to take that derivative of that with respect to x. Well, so that's derivative with respect to f with respect to y, then derivative of that with respect to x. Again, a second derivative, f, y, x. And we said in our class, our derivatives, we can take in any order, because for nice functions, it doesn't matter. And so the conclusion is that if you're conservative, that the derivative with respect to y of the first entry better match the derivative with respect to x of the second. Now, it turns out that if you're dealing with a two-dimensional vector field, or if you like, vector valued function, that's it. If these match, you're done. You're definitely 100% conservative. And if they don't match, you're also done. They're definitely 100% not conservative. And when you're not conservative, there's no shortcut. You just got to do the line integral. So you really hope for conservative. But that still leaves the question. How do we find the potential functions? So for that, there are two options. And here's the two options. The first one is what we've been doing for the problem so far, which is we say we take a look at what we have. We say, okay, we know what the derivatives look like. And we say, what should the function be if we took the antiderivatives of each little part and we piece them back together? And okay, once you've done that, you should check the answer. Now this says educated guess, which is to say, it's not hard to figure out how things should fit together. We're going to do some examples where we fit things together, which are not so trivial as what we've done so far. But you have to sort of pay attention. And if you do the method where you're just like, I'm just going to figure it out by looking at all the partial derivatives individually and sort of guess, always check your answer. That way we'll be confident that you knew what you were doing. If you just say, this is the potential function on an exam, we're worried that you may not know what you are doing. And so we can't give you all the credit. We want you to get all the credit. So just, if you do just method 1, make sure you check the answer. Then we'll be satisfied. Method 2 is to say, it's something more methodical. We're going to build it up a little bit at a time. And we'll talk about what we mean by building it up a little bit at a time. Right now. So here we go. So what we have is, if you want to build a potential function, you start by saying, I know the derivatives. So in particular, what I have here is that m, this would be my f sub x, and n would be my f sub y. So I say, if I want my function f, I go to my first entry, and I say, there's my derivative with respect to x. That's close, so let me just integrate that with respect to x, and I'll basically be done. Well, almost. So you have to be careful. Because think about what happens. If I start with something and take the derivative with respect to x, what happens to anything with a y in it? Well, it's treated like a constant, and so if it's only with y's, it goes away. So what happens is, in the first step, if I only use information about the m slot, I can get most of my function, except I might have other stuff left which only depends on y. So the question is, well, how do you figure out what that part is? For that, you say, okay, now let me take my answer, my current answer, take the derivative of this with respect to y. You'll have a c prime of y. But all that has to match n, because that's also the derivative with respect to y. And you're going to get your c prime of y. Well, once you have that, you can get c of y, and then you're done. You plug it in. Now, you might say, okay, why won't this always work? It sounds pretty foolproof, because we know that not all functions are conservative. Well, we actually don't know that yet. We haven't seen an example explicitly that says that, but you can take my word for it. Not all functions are conservative. If you have something which is not conservative, it breaks down at step 2. And the reason that step 2 will break down is you really need to get the derivative of y only in terms of y. And if it's not conservative, it won't happen. So try it out. But for right now, we need to focus on actually building things which are conservative, because we'll need practice. So let's do some examples. So we're going to find f, little f, our potential function, so that capital F is the gradient of f. So in other words, capital F is conservative. And we're told capital F, what is it? Well, 4x cubed plus 9x squared y squared times I plus 6x cubed y plus 6y to the 5th times j. Now, if you don't like this notation, it's okay to change it to notation you're comfortable with. You could also write this as 4x cubed, plus 9x squared y squared, comma, 6x cubed y plus 6y to the 5th. This is just another way to write that. Whatever way you're comfortable with, that's what you should do. Now, let's talk about the two methods. The two methods, not this one. We'll do that one second. The first method was say, let's look at these partial derivatives. Now, if I look at this partial derivative, I say to myself, well, this is my partial derivative with respect to x. So I need to figure out what should my function look like. So take the integral of everything you see with respect to x. The integral of 4x cubed with respect to x, x to the 4th. The integral of 9x squared y squared with respect to x should be 3x cubed y squared. Okay, now that's just in the first slot. That's what we're seeing has to be there. Now go to the second slot and do the same thing. What's the integral of 6x cubed y with respect to y? Because now I'm in the f sub y slot. 3x cubed y squared. Now you might say, that seems really familiar. It should. We'll point that out. Okay, but one more. Integral of 6y to the fifth with respect to y? Y to the 6. Okay, so that's what we get in our second slot. Now, how do we piece it together? Well, we basically say, okay, look, anything that's just a function of one variable, that certainly has to be in our final answer, so x to the fourth. If something has more than one variable involved, it better be in both locations. So you can see that it's consistent. I get a 3x cubed y squared in one part, I get a 3x cubed y squared in both parts. I only need one of them, because what's going to happen is each different derivative is going to see it because it has both an x and a y in it. Y to the 6, we're still going to need that. And lo and behold, there we go. So here's our potential function. This is our f of xy. And now we can check gradient of f. Well, we have a derivative of x to the fourth is 4x cubed. Taking derivative with respect to x right now. Derivative of 3x cubed y squared. That's 9x squared y squared. Derivative of y to the 6 is 0, comma. Now repeat with respect to y. Derivative of x to the fourth is 0. Derivative of 3x cubed y squared would be 6x cubed y. And derivative of y to the 6 is 6y to the fifth. And we match, so we're good. So that would be the look at the partial derivatives and piece it together. And the key is just to say, hey, things should sort of mingle if I see multiple variables involved, and there should be a consistency. So the fact that I saw 3x cubed y squared said I better have a 3x cubed y squared again. All right. Now, what if we did this process? Well, this process says the following. My function f is going to look like the integral of 4x cubed plus 9x squared y squared dx plus something which depends on y. Now, if I take the integral of 4x cubed plus 9x squared y squared with respect to x, what do I get? X to the fourth plus 3x cubed y squared plus some function which depends on y. And the reason I'm using C, I'm doing that quite deliberately. I'm thinking that that's my constant. It's my constant. In this case, it's a constant function. Okay, so that says my function better look like that. I just have to figure out what this last piece is. And to do that, I now say, well, take the derivative of this with respect to y. Derivative of x to the fourth will go away. Derivative of 3x cubed y squared will be 6x cubed times y. And the derivative of my constant function of y is c prime of y. Well, that better be equal to what the derivative with respect to y is, which is 6x cubed y plus 6y to the fifth. So this is my n, if you will. Now, we start and say, cancellation. Aha! The 6x cubed y terms are going to knock out each other. So we can conclude that c prime of y is equal to 6y to the fifth. So this is what we're talking about here in the second step. Get that c prime. So if I take the derivative of c of y, I get 6y to the fifth. So what does that say about my original function c of y? Y to the 6. Now, y to the 6 plus some constant. I just pick a constant I like. I really like 0. 0 is a great constant to pick. So, finally, what I do is I take this and I put it back in to my c of y. So that I get that the function is x to the fourth plus 3x cubed y squared plus y to the 6. And because this was built up methodically, we don't need to check. We know that this is going to work. All right, so those are the two different methods to find that. All right. Well, we've been dealing with vector valued functions with 2, vector valued functions with 3, same ideas. It doesn't really matter that we started with the two-dimensional picture. Nothing was very two-dimensional in our argument, so it works in 3 dimensions, and 5 dimensions, and 9 dimensions, however many you need. So the integral along the curve of a gradient of f dot dr, you take the function at the end minus the function at the start, where the function is the potential function. Now the only big difference of what we talked about so far is how do you find that potential function, or how do you know that something is a conservative? Well, previously we only had to look at the two pieces m and n and say those derivatives are somehow compatible by checking what would happen if we went a little bit deeper. Now we have a lot more derivatives, so there's a lot more things to check. So it turns out that there's 3 things to check. Now, if you go through, another way to put all that into checking is just to say take the curl, and if the curl is 0, it's definitely conservative. Now, to be honest with you, most of the time we never even bother to test if something is conservative because we have a slightly different approach. We say something is conservative, well, if we can find the potential function. So if we find the potential function, we don't have to check. So we only go to this extreme if we have some reason to suspect something is conservative, but we don't have a good way to find what the potential function is. All right. So let's try this again. We want to find a potential function to the following expression. So our function e to the x cosine y plus yz, xz minus e to the x sine y plus 2y plus z e to the yz, and xy plus y e to the yz plus secant squared z. Oh, this looks good. Which method would you prefer? There were 2 methods we talked about. Sort of the method 1 was like take the antiderivative of each slot, just make sure they mix together, and then check your answer. Method 2 was work up one at a time. Do you have a preference? 1? Okay. I can do both. But let's start with 1. So, we're going to work through each slot and say, okay, this slot, this is our f sub x. So, let's see what our function f should have. So the parts of our function which involve the variable x will need what? Well, if I take the derivative of e to the x cosine y with respect to x, what do we get? E to the x cosine y. If I take the derivative of yz with respect to x, what do we get? xyz. So our function better have these 2 pieces in it. Now let's go to our next slot, which is a very long slot. That should be the derivative with respect to y. Excuse me. So let's go through again and look at each piece. Antiderivative of xz with respect to y, xyz. Antiderivative of minus e to the x sine y with respect to y, plus e to the x cosine y. Antiderivative of 2y with respect to y, y squared. Antiderivative of z e to the yz with respect to y, e to the yz. So our function better have all those pieces in it as well. And now we come to our last slot. This will be our derivative of our function with respect to z. All right, so the derivative of xy with respect to z, xyz. Derivative of y e to the yz with respect to z, e to the yz. Antiderivative of secant squared z with respect to z, tangent. So now what we do is we start piecing our function together. So our function f, well, should have all the stuff that came from the first slot, e to the x cosine of y, plus x, y, z. Now I go to my second slot and say x, y, z. Well, I already have an x, y, z, so that's already been taken care of. And I should have expected that because it should be compatible. And I have an e to the x cosine y, which is actually a good sign. I don't have the y squared yet, so let me put that in. E to the yz, don't have that yet. I better put that in. All right. Now I go to the next slot, the third slot. The x, y, z, I've already got one of those. And it's okay that I see it 3 times because see, it involves each variable, x, y, and z. So I should expect in each derivative for it to show up. The e to the yz, we already saw that because that also had a y in it. We don't have the tangent of z. So we add it. Tangent z. And there's our function. But how do we make sure? We check. How do we check? Take the gradient. And I know you're probably going to say, aren't you just going to write down the gradient from before? Well, I'm going to pretend like I'm actually taking the gradient. But if we've done our job right, lo and behold, if you go through, take all these partial derivatives, we're going to see that there's a lot of compatibility with what we've done. In other words, it really does work out. And it's good to double check. See, double checking, make sure you don't accidentally overlook something like, ooh, I forgot that. I better go back and make sure I didn't make a mistake. So even though you're very confident of your answers, you should always double check. Ah, yeah, and it worked out. Okay, good. Life is good. All right. Let's try another problem. Okay. Suppose we have a conservative function, but for some reason that you have trouble finding the potential function. Well, it can happen. We learned in Calc 1 and really learned it in Calc 2, there's a lot of stuff that's hard to integrate. So, hope is not all lost. Because we said that there was a second thing we could do, which is we could change our curve. So if we have a potential function, if we have something that's conservative, we're not having much luck finding the antiderivative, let's change our curve. And maybe let's work by seeing what happens along the curve. There's still a chance. All right, so here's an example. Suppose we're integrating along a particular curve. So the curve here, it actually gives us a curve. Cosine t, 2 sine t. Do we have any idea what that looks like? Suppose you didn't see the 2. You saw a cosine sine. What would it be? It's a circle. So the 2 is only multiplying by the y coordinate. So it's like you're stretching in the y direction. So it's almost as if you take the unit circle, but instead of going 1 up to 1, you're going to go 1 up to 2. So it's a stretched out circle. It turns out, not important to the problem, this is part of an ellipse. It doesn't really matter. The important thing is we have the curve. And where do we start? Well, time 0, you start at 1, 0, and at time pi halves, you end at 0, 2. So our curve is doing that. Here is C. Now, we're trying to find the integral along C of y squared arctangent x cubed y to the 6 plus y e to the x dy plus 2xy arctangent x cubed y to the 6 plus e to the x dy. Okay. Well, I already see arctangent. I know this is going to be a really cool answer, but I also feel like, I'm going to have a problem. What's the antiderivative of y squared arctangent x cubed y to the 6 with respect to x? Yeah, but there's that x cubed in there. This is not looking promising here. Similarly, if you said, okay, well, can you take the antiderivative of 2xy arctangent x cubed y to the 6 with respect to y? And well, let's check if it's conservative. So we're going to call our first slot M, our second slot N, So let's check. What would be m sub y? Because this is already the derivative with respect to x. I'm going to go to the mixed derivative. So if I took the derivative with respect to y, well, derivative of y squared is 2y. Then arctangent of x cubed y to the 6 plus y squared times the derivative of arctangent. That's 1 over 1 plus x cubed y to the 6 squared times the derivative of the inside with respect to y, which would give us 6x cubed y to the 5th. And finally, we take the derivative of y e to the x with respect to y. Well, at least that one's easy. That's e to the x. Okay, so that's what happens when we take the first slot, take the derivative with respect to y. When we go to the second slot and take the derivative with respect to x, well, product rule again. Derivative of 2xy with respect to x is 2y. The arctangent stays as it is. So arctangent x cubed y to the 6 plus 2xy, maybe it's not conservative. Derivative of arctangent's 1 over 1 plus x cubed y to the 6 squared times the derivative of the inside, which would be 3x squared y to the 6. And derivative of e to the x with respect to x is e to the x. Do these match? E to the x's certainly match. Arctangent's terms match. And if you stare, you'll see you get a 6 x cubed y to the 7th. They do match. So my is equal to nx, which means we are in fact conservative. But we'd have a hard time finding that antiderivative. Okay, so we got to try to change our approach. So we're not going to try to find an antiderivative. Well, I think we know where we're heading because it kind of told us what to do here. What should we do? What?
Look for a better curve.
We should look for a better curve. Now you might say, wow, how do we know that? Well, again, it says it right there. Now, what would be a better curve? And here's sort of the interesting question. It's not a priori, in other words, from the start, it's not obvious which is the better curve. A lot of people would say, oh, just go in a straight line. But straight lines are sometimes great, but they're not as good as they could be. Here's how I like to look at it. Try to choose a curve which will make the integral easy to work with. And so we say, what things make integrals easy? And the thing that makes integrals really easy are zeros. So try to find stuff that makes stuff zero. In particular, 0 often makes things 0. So, with that in mind, we are going to pick a curve that hugs the axes. So it's going to go straight across, and then we're going to turn 90 degrees and go straight up. I'll call this curve 1 and curve 2. Now, suppose we do the integral along curve 1. Let's see what happens. Well, what's the parameterization? If we think about the parameterization, so we really are truly doing a line integral. So we're going to have, our parameterization can be 0, minus t, or well, we'll say t, and t goes from 1 to 0. So in other words, we're going to run time backwards just because our curve is sort of going in the opposite direction. But we need a parameterization. And I see I screwed that up because it should be t comma 0. Because I should be on the x-axis. There we go. Now I did it right. Well, what happens to our terms? What happens to the arctangent of x cubed y to the 6? It becomes 0. Because I'm going to have a 0 on the inside, arctangent of 0, 0. What happens to the y times e to the x? It's going to be 0 because y is 0. So this is 0 and that's 0. So okay, that term goes away. What happens here? Well, here, still 0. E to the x Well, that's going to depend on x. It'll be e to the t. But what about dy? What is that? It's 0 because there's no change in y. So the integral along curve 1 is 0. So, well, it becomes 0. All right. Yeah. Well, 0. Okay. The point is, everything zeroes out. Life is good. Properly, I really should say the integral along the curve 1 of stuff is the integral from 1 to 0 of 0, which is 0. Okay. Let's talk integral along curve 2 of, we'll be more precise here, stuff. I don't want to copy it down again. So what's our parameterization along curve 2? 0t, where t goes from 0 up to 2. So this is our curve 2. So we go from 0 to 2. So let's plug it in. Now remember, everywhere you see an x, you put 0. Everywhere you see a y, you put t. What happens to this term? The y squared arctangent x cubed y to the 6 goes to 0. What happens to y e to the x? It goes to t. Yes? Because y is t, e is 0 is 1. dx will become 0. Oh, that was kind of disappointing. Okay, plus, which means that's all gone. The next term, 2xy arctangent x cubed y to the 6, what will that be? 0. Plus e to the x, which is 1, and dy is dt, because y is t, derivative of y is 1. And so, if we simplify, this is the integral from 0 to 2 of 1, which is 2. So our original integral, which looked a little bit daunting, by changing our curve, became not so bad. So you should be suspicious. If you can find a potential function, but you think it's conservative, can you find a better curve? All right, well, pick up again later. Well, maybe just a little bit more practice would be good. So here we go. Let C be a curve that joins 0, 0, 0, and 1, 1, 1. So here we see we're in 3 dimensions. All right, so what's the curve? Well, it's some curve. We don't know. We know where we start, and we know where we're going. So we have the point at the origin, 0, 0, 0. And then we have a point out here. Let's say this is at 1, 1, 1. And we're going from 0, 0, 0 to 1, 1, 1. And it's some curve. Now, once you see that it's some curve, but they don't specify the curve, you should already be like, well, it's got to be the case that this must be something truly special to be able to just work. All right, you know, for example, there's a curve. Is it that curve? It's a curve. Now, obviously, if we were going to do this in real life, we would say, look, if they didn't tell us anything else, pick the straight curve. The straight curve is usually the easiest. Unless, of course, there's some reason while we're going along some other direction, it might be easier. So we suspect to begin with that what we're dealing with is a conservative function, which means that the part attached to dx, we think this should be a derivative with respect to x. We think that the part attached to dy should be a derivative with respect to y, and the part attached to the dz should be some derivative with respect to z. So let's do method 1. Remember what does method 1 say? We want to build up the function, and we're just sort of going to say, what do the partial derivatives look like? And then make a guess by combining this all together. So I integrate the first piece with respect to x. The integral of 2xy with respect to x is x squared y. And the integral of z cosine x with respect to x is z sine x. So I'm going to switch colors here as we move across. So now let's take a look at the second term. The derivative of the function with respect to y gave us x squared plus e to the z minus sine y. So x squared y, because I'm taking the integral with respect to y, e to the zy, and then the integral of minus sine y is plus cosine y. Okay, now to the last integral. Well, for here, we're going to integrate with respect to z. So we're going to get y e to the z. Oh, that's y e to the z. Integral of 3z squared, z cubed. Integral of sine x. Well, sine x is a constant when I integrate with respect to z. So it'll be z times sine x. Now, what do? To get our final answer, we put them all together. So we just want to make sure they're compatible. So we say, okay, we start with f. And to be compatible, we just want to make sure if something involves multiple variables, then it shows up in all the places. So for example, x squared y shows up twice, because it should show up with respect to x and it should show up with respect to y. So we got the x squared y. We don't need to do it twice, we just need to get it once. So we already caught that one. Z sine x. Then we have e to the z times y. I'll put the y in front. Y e to the z. The cosine of y. Then we come to y e to z, but we already got that because it showed up here in the derivative with respect to y. Then we have the z cubed. And then we have z sine of x. But notice that already showed up, so we don't need to put it again. All right, so there's our function. Well, at least there's the candidate. Of course, it's right, but we check. So what do we mean by we check? We take the gradient of this just to verify. So the gradient is, with respect to x, well, 2xy, z cosine x, and 0, 0, 0, comma, with respect to y. X squared, 0, e to the z, minus sine y, and 0, comma. Here with respect to z, 0, sine x, y e to the z, then 0, and 3z squared. And if we compare the entries, we see they match up. It's okay if the order of addition doesn't matter, because you can add in any order you want. So, we've now found the potential function. It is conservative. Good. So what do we have? Well, the integral along the curve of the stuff is going to be the function x squared y plus z sine x plus y e to the z plus cosine y plus z cubed evaluated at the endpoint. So 1, 1, 1, 0, 0, 0. So we plug in 1, 1, 1. So we're going to get 1 plus 1 times sine of 1 plus 1 times e to the 1 plus cosine of 1 plus 1 cubed is 1. Subtract, plug in 0. Always got to double check because occasionally things sneak through. 0 and 0 and 0 and, oh, see, cosine 0, 1 and 0. Okay, so the good news is we get a little bit of cancellation. We can knock off a single 1. All right, and the zeros go away. So we're left with 1 plus sine of 1 plus cosine of 1. We're like thinking to ourselves, hey, sine of 1 plus cosine of 1, that's sine of 1 plus cosine of 1. Be careful, remember your identities. It's sine squared plus cosine squared. Simplifies, but not sine plus cosine. And there we go. There's our answer. Now, that's not so bad. In fact, these problems, the moral of the story is, they're not. They should actually be kind of fun, because it's just a matter of sort of figuring out what it is the problem is asking and putting it together. However, you might say, it wasn't so bad because we didn't have a hard time finding the potential function. Now here we said, well, let's look at what the partial derivatives give us and mix and match. What would the other way to do it, which is to say that we're going to build up? So let's go through the building up variation. So we're going to go through this. So what we currently have is we're going to work our way through all three of these and see what we get. So we start by saying, well, let's just use the first entry. F sub x is 2xy plus z cosine of x. So now if I want just f, the function, I integrate with respect to x. Now here's the key. When we integrate with respect to x, we treat the other variables as constant. That's half the key. And so doing that, what do we get? Well, we get x squared y plus z sine x. So that's not the hard part. The other part of the key is to say, but what was the constant here? So when I took the derivative with respect to x, the constant is anything which would vanish when I took its derivative. So for instance, constants are numbers, functions evaluated numbers, but also anything that involves just y and z. So it could be a combination of y and z. So what you have is now you have as your constant not a number, not a constant function of one variable, but a constant function of two. So just from the first slot, I can recover what the function looks like, up to there's a piece I don't know. And then we say that's no problem. Now we go to slot number 2. So for slot number 2, I start by saying, well, let's take the derivative with respect to y. So derivative with respect to y, we're going to do in two ways. First off, we come to our expression here, take derivative with respect to y. So I get an x squared y, that derivative is x squared. Derivative of z sine x, well, no y, so it goes away. Derivative of c of yz, well, that's going to be a partial derivative, c sub y of yz. Now, what does this equal? Well, it equals the second slot, x squared plus e to the z minus sine y. And what do you notice? Well, the x squareds are going to cancel. So we can conclude from this that c sub y of yz is equal to e to the z minus sine of y. Okay, so now we have a partial derivative, but really it's a partial derivative, and there's two variables involved. It's actually a better situation. If you think about where we started, essentially we had three variables involved here. Now we have two. We're working our way down. So we integrate with respect to y. So we get that c is the integral of e to the z minus sine y dy. So that's going to be e to the z times y. Integral of sine is cosine y, and then anything that's constant with respect to y. So that's going to be some constant function of z. My only variables right now are y and z. I've already used the symbol c, so I'll just work my way up the alphabet. d of z. So let's update. I know what c is. So when I say let's update, what do I mean? I mean let's take this information here and plug it in there. So we can now say, by combining the information from the first two slots, we have that f is x squared, x squared y plus z sine x plus this part, e to the zy plus cosine of y plus something that depends only on z. Okay, good. So see, once we start here, once we use this information, we had two variables that we still had to resolve. Now we have just one variable to resolve, and we still have one entry left. So we swap gears yet again. All right, now we're going to look at the next slot, which is the derivative with respect to z. Come along here, read off the derivative with respect to z. Well, there's no z in the first entry. Here, we're going to get sine of x. Derivative of e to the zy will be e to the zy. Cosine y, there's nothing there. Plus the derivative of z. Derivative of d of z. So that would be d prime of z. What will that equal? Well, it equals this part right there. That's the derivative of the function with respect to z. So that's y e to the z plus 3z squared plus sine of x. Now, we see we get some cancellations. The sine x's cancel, e to zy and y e to the z are the same. So that allows us to conclude d prime of z is 3z squared. Well, now integrate. What is d of z? Well, it's z cubed plus some constant. Well, at this point, choose a constant to be 0. Okay, so that's gone. Now, what do we do with this? We update. So, we can say now that our function is equal to x squared y plus z sine of x plus e to the zy plus cosine of y plus z cubed. And we're done. We built it up, one layer at a time. Did we get the same as before? Well, let's check. We got the x squared y, z sine x, e to zy, y, they're both those same. Cosine y, z cubed. Yeah, okay. Well, which method works? Well, they both work. You just have to choose which method works best for you. In some sense, this is a little bit longer process. It's more methodical, and but you get to the same place. This process here, it has sort of a built-in checking mechanism, so that once you're done, you're confident. Whereas in the other process, where you say, well, let's look at seeing what the parts would be and piece them together, it's a little bit more fuzzy. And so if you do choose to go in this route, do double check that you got all the pieces put together correctly. Check your gradient, because remember, our goal is to get all the points. All the points. All right. Now, let's do a little bit of theory. It's good to understand things. We know that line integrals for conservative functions are nice. Okay. Now, you might say, is there anything else nice? So in other words, are there any other functions which are not conservative where it says, hey, it doesn't matter what you pick? In other words, it doesn't matter which curve you choose to go between 2 points. You're always going to get the same answer. And the answer is no. So not only is it that line integrals are nice for conservative functions, line integrals are only nice for conservative functions. Any other function, you have to be careful, because it can change depending upon what curve you use. I'm not saying it's always going to be a different answer, but it could be. There's always a curve which will give you a different answer. So be careful. Now, why do we say no? Let's take a couple of minutes and just talk about the theory. So here we go. The following three things are equivalent. 1, our function is conservative. In other words, it's the gradient of something. 2, the integral of the curve of our function depends only on where the endpoints are. So it doesn't matter how we get between 2 points. So in other words, this is what we mean when we say something is nice. If I always get the same answer regardless of which path I choose, that's nice. And the third option, or the third thing which is equivalent, is that the integral is always going to be 0 if I ever have a curve that loops back to where I start. So in other words, if I'm close, start equals stop, the integral will always be 0. So those are equivalent. Now, what can we say? Well, we've already seen that if f is conservative, then it's the case that the integral only depends on the endpoints, because we said that you take the function f, the potential function f of b minus the potential function f of a. So we can see that 1 implies 2. That's what we did at the very start. But 2 and 3 also are easy to tie together. So there's 2 important ideas. So remember, important idea number 1. That is, if I start on a curve, say here's A and here's B, and I go forward, and if I compare that to the same curve where I go backwards, so I start at B and I end at A. It's the exact same curve, I just changed the direction I travel. These have opposite orientation, and the important thing is that when you reverse the orientation, that this means that you're going to change the sign. So where one is positive, the other one will be negative. Where one is negative, the other one is positive. In fact, that's the only thing that changes. So whenever you change the orientation, you're going to change the sign. Orientation is going to be really important in the next couple of lectures. So, how is it that 2 and 3 tie together? Well, suppose, for a moment, I have the following. Here's my point A, and here's my point B. So, I have one curve that goes from A to B, and then I have another curve that goes from A to B. So there's C1 and C2. Well, what's true? If it doesn't matter what endpoints I pick, it means the integral along curve 1 of whatever is the same as the integral along curve 2. Well, all right, that's f dot dr, f dot dr. Now, here's the key. Let's flip it. So, I have A, I have B, I have my curve 1, and now, instead of doing that, I'm going to go the other direction. And probably shouldn't have picked so many waves. All right, but this is C2 in reverse. So I can actually write that as minus C2, just to emphasize I went backwards. Well, let's take a look at what happens. I can say that the integral along this whole curve, so I can say the integral along the whole curve, I'll call that C, of f dot dr, is 0, because I start and stop at A. So if I take C1 and C2 backwards, I always get back to where I started, so the integral is 0. But this is the same as the integral along C1, and then the integral backwards along C2. And the backwards says flip the sign. So you get f dot dr, but minus. And now we're done. That's actually it. That's how we can tie 2 and 3 together. Because what does this say? If the integral along the curve is 0, these two have to be the same. If these two are the same, the integral along the curve is 0. So that's how you show 2 and 3 they link up. They're the same. All right. Well, what's the interesting part? Well, the interesting part is to say, well, suppose I know fact 2. Well, the integral only depends on the location of the endpoints. It has to be the case that what I started with is conservative. Now, how does that work? The answer is, you have to think about it. Here's what it is. And, well, all of text here, but let's just think about what's happening. I have to show that there's a potential function. So I have my vector value function, f. I want to find my little f. And I just make one. And the function says, look, I'm going to start at the origin, and I'm just going to go to the point xy. And I'll just take any curve. And why can I take any curve? Because it doesn't matter which curve I take. See, that's why it works so well. So I'm just going to move along any curve from 0, 0 to xy, and I say, what's the total? What do I get? Whatever I get, that's the value of the function. Now, this is kind of an interesting idea to define a function this way, because at some point it feels like it's kind of ambiguous. We're used to having a machine, but it does work. So a function just says you have to have a rule that says you give me any xy, I'm always going to get a consistent answer. So here, the rule says, look, if I start at 0, 0 and go to xy, because of my assumption, I'll always get a consistent answer, and therefore it really is a function. Now, what's our goal? Well, we want to say somehow that if I look at this f, this m right here, we think, does this equal f sub x? Well, maybe. If it's true, it should. And we want to do something and say, does this equal f sub y? You know, we don't know yet. That's what we want to show. So here's how you do it. We're just going to do one case. So I'm going to try to take the partial derivative of f with respect to x. And so for right now, I have a fixed point in mind. So I'm thinking, here is my point x comma y. And I'm just going to fix some x value, x naught. So I'm always going to have two pieces. The curve C1 it's fixed. It's not going to change. Then I have a curve that goes straight across. So it always is on the same y value, and it goes from x0 to x. This is very easy to parameterize. So how do you parameterize it? Well, it's t comma y, where t goes from x0 to x. Now, what's the value of the function? The value of the function is you go along C1, so that's the first piece, plus you move along C2. We use the parameterization. There's no y change, so n dy goes away. So then we have m, but we use the parameterization ty, and dx will become 1 dt, so that's where the dt comes from. And we're going from t equals x0 to x. So this is the parameterization of C2. Again, I'll write it down. Its parameterization for C2 is t comma y, x0 less than or equal to t less than or equal to x. So we have that part right there. Now, take the derivative with respect to x. If you take the derivative of this side with respect to x, you're going to get f sub x, because that's what you get. It's the derivative of f with respect to x. Take the derivative of the first term. Well, this doesn't depend on x at all. See that? Note it's constant with respect to x. Gone. Gone. Come to this part. Take the derivative with respect to x. The only place where x shows up is up here. Now, use the fundamental theorem of calculus. The derivative with respect to x of integral from some constant to x of f of t dt is f of x. It's that function when you plug x in. So that means we're going to get m. It's m. So from f of x, we get m, which means that this is, in fact, f of x is m. And similarly, f sub y is n. So that's it. That's how it works. Now, this is just for your information. We don't really test on it. It's just a reminder. Look, we like conservative functions because they're nice, and we want to deal with them as much as we can. And we really do mean conservative functions are the nice functions. And if you're not conservative, you're not quite as nice. Now, in fairness, we've really spent almost the whole time today talking about conservative functions. So let's, for a moment, actually give at least one example just to show not everything is conservative, and talk about the various things that might happen. So let's make our capital F function. And what should we make it? Well, let's make it y over 1 plus x squared y squared plus y, comma, x over 1 plus x squared y squared. Now, I claim that this function is not conservative. Well, let's see. How can we prove that? Let's call this m, and let's call this n. And if we do this, well, we look at what is m sub y. According to the rule, we would take, well, okay, let's think about this. This would be 1 over 1 plus x squared y squared. So I'm taking the derivative of y. And really what I'm thinking this is y times 1 plus x squared y squared to the minus 1. So derivative of the first times the second, plus, then I'll have y times minus 1 times 1 plus x squared y squared to the minus 2, which will go downstairs, 1 plus x squared y squared, squared, times the derivative of the inside with respect to y, which will be x squared times 2y. Then plus 1, derivative of y. Now, if we do n sub x, we're going to see something very similar. 1 over 1 plus x squared y squared, and then the other term is going to be what? Well, it's going to be x minus 1 over 1 plus x squared y squared times 2x y squared. And if we stare at this for a few minutes, we'll see these pieces match, and these pieces match, but there's nothing down here to match. So this is a case where m sub y does not equal n sub x. So this is not conservative. Now, you might think that I chose a rather complicated example to get to where we're at, and in some sense I did, but I want to talk about a few things that are true. Let's talk about a few things that are true. Suppose I wanted to create a potential function. Well, how would I go about doing it? Well, so suppose I ignored for a moment that this was a conservative, that this was not a conservative function. I'm looking for something that has a nice antiderivative. It's actually not too hard to find a nice antiderivative in this case. So if you integrate this with respect to x, it basically looks like 1 over 1 plus the quantity xy squared. Or 1 over 1 plus x squared is a better way to think of it. When you see that, you're like, oh, that looks a lot like arctangent. And so if you integrate this with respect to x, and you sit for a few minutes and think about it, it would seem that you'd get arctangent of x times y. And indeed, that's where it came from. Okay, it's not too hard to verify. And that's what you get. And then if you integrated this part with respect to x, you'd get plus xy. So that's if you integrated the first term, the m term. Now, if you integrated the second term, what would happen? Well, you'd still get the arctangent of xy, but then you wouldn't have anything else. And here's the problem, is when you went to go put these two pieces together, you'd say, oh, look, these are compatible, yes, but then it's like, uh-oh, there's a problem. See, there's an xy here, but there is no xy there. This should have shown up in both places. So that's why this one is sad. It's not going to work out. So that's how you would see a problem. Similarly, if you went to try to go through and do it a more methodical way, you'd run into trouble. Now, at this point, you're probably thinking, okay, so is all hope completely lost with this function? And I would say no. One thing you can do, and this is one thing to look for, is you can say, well, maybe it's partly conservative. And it's not all conservative, but maybe we can say, look, part of it works really nicely. So, for instance, you can take the function, and you can think of it as saying there's two parts. There's one part that looks very nice, y over 1 plus x squared y squared, and x over 1 plus x squared y squared. That part looks really nice, because that's the part that had that compatibility when I tried to do antiderivatives. Plus, there's another part, y 0. Then you say, okay, well, this part, that's the gradient of arctangent of xy. And then you have this other part, y 0. And what's the moral? Well, it says, suppose you had to do something. Well, you could say, I can use conservative functions to handle this part. And I can say, let me go through and work it out. And so this might help simplify it to see what that does. And then the other part that says, well, with everything else, okay, this remaining part, well, I can't use the properties of conservative functions. It means I can't change the curve. I can't look for a potential function. But the remaining part might not be so bad. So just because you say, it's not conservative, okay, throw it all away. No. Try to use as much as you can. It's possible that you can still make good progress in this case. All right, so be careful. Not everything is conservative. A lot of things do turn out to be conservative, and maybe that's one of the beauties of the world, that things turned out so well. All right, good. Keep working.